Our next presentation is by Jan Kabatek from the University of Melbourne. Jan is going to be presenting efficient commands for data visualization in large data sets. So please welcome Jan to present his paper on efficient commands for data visualization in large data sets. Jan, over to you.
Thanks a lot, David. Let me just try to share the screen. Excellent. So yeah, thank you so much for having me. I have to say that I'm quite excited about this. This is my first Stata conference and definitely my first Oceania Stata conference. And just a bit about myself, I'm a research fellow at the University of Melbourne. My background is in econometrics, and I'm mostly dealing with really large data sets. And that's also what this presentation will be about. I should also probably mention that my presentation will be quite simple. It's definitely not going to have any technical aspects to it. I mean, in principle, it could be done in 5 minutes. But given that I have more time on my hands, I decided to make a little bit of an appeal for kind of general efficiency in statistical programming. And I'll tell you why. So I'll start with a question which is not really asked that much in our profession. And that is whether you have ever wondered about the environmental costs of your work. Now, I'm asking that because we do spend most of our time analyzing huge swaths of data, and that of course requires a lot of computing power. Now, computing power obviously translates into electricity consumption, and this consumption translates one way or another into carbon footprint. And the underlying question is, well, okay, so there's a carbon footprint, but how large is it? And if it's large, what can we actually do about it? And I have to admit that it's not easy to find data on this, but we can look into other disciplines and draw some inspiration from what they have found. So here's this paper, very recent paper by Stevens and co-authors, which appeared in, I believe, Nature Astronomy. And this paper assessed carbon footprint of Australian astronomers. And they basically found that the carbon footprint of computing alone per researcher is about 22 tons of CO2 emissions per year. Now, this might not seem like a meaningful number, but sure enough, it was the single highest contributing factor to their overall carbon emissions. And just to put it a little bit into comparison, you can read here that average American household, right, household, not the person, produces about 7.5 tons of CO2 emissions per year. So that's quite a bit higher. Now, of course, the carbon emissions of people who use statistical softwares like Stata are probably different from those of astronomers. After all, astronomers do tend to rely on supercomputing quite heavily, but it's not really clear whether they would be that much lower because, you know, mind you, this number is essentially averaging over all researchers within the field, and not everybody is kind of engaged in these computing heavy operations. And on top of that, if you factor in the much larger base of users of Stata, then we're definitely entering something of a zone of non-trivial emissions, which we should be mindful of, okay? And I think that based on this, we should be putting quite a lot of effort into making our software packages as efficient as possible. But as I said, you can also get the compass bin if you're that way inclined. Now, this presentation will be a very simple conversation starter. I do want to highlight that there is quite an environmental imperative of efficiency when it comes to statistical computing. And I want to illustrate it by this user-written family of commands that I have produced, which is called plot. These are graphing commands which overcome one of the most kind of pernicious bottleneck that we can see in current versions of Stata, and I'll basically talk about how to address these things. All right. So just to set the stage, I'll start with a simple example. As you can see, it's very basic. We're just using the default auto dataset, and we are making one histogram, right? Now, this command is very fast. On my machine, it takes 0.8 seconds to run, which is great. But now let's see when we amend this command a little bit and expand it by 4 million times. So instead of 47 observations, we have 47 times 4 million observations. And we will just parse the same command into Stata. Now, in this case, the command takes half an hour to execute. And you might be thinking, well, obviously, you've added so many more observations. Stata is basically just spending all this time on computing the histogram bins in this much larger data set. But that's actually not the case. The execution times and their length are partially attributable to this bottleneck, which I was referring to. And just to illustrate this bottleneck, I will present a very stylized workflow of the histogram routine. Now, I should also state that I didn't really check the underlying do file that corresponds to the histogram command. So this is more of my impression of what I think is going on under the hood, okay? So this workflow goes as follows. First, the command preserves the original data set, the huge, 100 million observations data set. Then the command calculates the bins of the histogram, which are to be plotted. It stores these bins as a temporary data set, effectively replacing the original one in the memory. And then it displays the corresponding graph, okay? Now, finally, the command restores the original data set into memory. Very simple workflow, but there's a problem with that. And that is that preserving and restoring these big data sets can take forever. It can take hours, literally. And this was kind of an inevitable issue in earlier versions of Stata, but as of Stata 16, this is basically redundant, because now we can leverage the new environment of data frames. And as a result, we can store this kind of auxiliary histogram bin data as a separate data frame while holding the original data set also in memory. So there are no kind of computationally heavy or memory heavy operations going on in the background. We're essentially kind of dropping these two steps. And that's basically the key change that underlies the efficiency gains of this plot family of commands that I have coded. Just simple information about the commands. Right now, you can download them from my GitHub. There is no SSC routine just yet because I do not know how to do that. And the pack of commands, which is on my GitHub, includes 4 routines: plot tabs, plot means, plot area, and plot B. And they're all variations on the same theme, producing slightly different versions of graphs. Now, these routines are extremely fast, as I will show you at the end of this presentation. And they also operationalize some other features which I was missing from the standard visualization packages of Stata. Most importantly for me and my workflows, these commands essentially store the data that I'm plotting in a dedicated data frame. And this data frame can be then later appended by other plots and other, let's say, lines or charts. And then I can use the same command to visualize all these lines and charts at once which means that I'm able to create very kind of complex visualizations of complicated data systems. So I'll just show you a few examples of these commands. First of all, I'll start with plot tabs, which is effectively doing tabulations, or kind of, it's visualizing the one-way and two-way tabulations, okay? Now, this is essentially equivalent to producing histograms with discrete bins, as you can see from this picture. But then you can basically add more histograms on top of each other, layering them and also comparing them, which is kind of nice. The Stata code that is used for this routine is here. As you can see, I'm basically replicating the same command twice, which is slightly clunky syntax. But once again, I'm not a good Stata programmer. This is basically just something that I came up with. And I should also say that I'm not showing you all the options which kind of specified the titles and axes and colors and stuff like that. So this is the bare bone setup. And this is essentially what we are plotting, right? Now, the plot tabs can also do conditional rates, similar to the command tabulate two-way with an option row and no frag, which means that you are essentially creating rates of dummy variables conditional on some value of the underlying conditional variable x, right? Examples of this could be, for example, employment rate. You could plot employment rate conditional on people's ages. And once again, because you can lay over different charts, you can plot conditional rates of employment for women, for men, and do all these comparisons. And everything is stored in the memory for later use. Now, plot means does a slightly different thing, and that is that it plots conditional means. So here I was plotting just the tabulations or the rates, and here I'm essentially expanding this toolkit to continuous variables, right? So rather than employment, we can start thinking about wages, and what are the average wages conditional on, let's say, age or educational attainment. Just to kind of explain the picture, what I'm plotting here is the means of a specific outcome. Y for 10 groups of individuals, which are labeled as G. And once again, all these means are conditional on X, which ranges from 0 to 800. Each and every line corresponds to one of these groups. And once again, this is really nice if we want to compare, let's say, the wage profiles of different people over their lifetimes, or let's say, average years of education by age, stuff like that. Now, as you can see, most of my examples will be econ related because that's where I'm comfortable with. But of course, you could extend this easily to sociology, to epidemiology, whatever you want. Okay, plot area is a command which plots what I call conditional share plots. This essentially means that we have a categorical variable, like a membership of a specific group. Here I'm plotting 4 groups, and I want to visually express what is the proportion of people with a specific value of X that belong to each of these groups, okay? So of course, the share ranges from 0 to 1. And then you can see that people with X equals to 0 are about 50% likely to be in group 4. And these membership probabilities decline as you move further, and it's kind of replaced by a larger probability of belonging to group 1. Once again, multiple applications. You can, for example, express how many people have different education levels, conditional on their age, or conditional on time. I've also included a criminology example. You could, for example, do a share of types of felonies over time or over population density, kind of comparing what kind of crime is taking place in cities and what kind of crime is taking place in rural areas. So that's what the plot area does. Now, plot B is basically another addition to this family. It plots sets of coefficient estimates. And this is nothing new. This has been done over and over again. Ben Jan has got the coefplot command, which is excellent. I just typed this up because I wanted to have something that has got the similar syntactical structure, and also which is less verbose and has got a less steep learning curve when it comes to the actual implementation. What I'm doing here in this example is I'm plotting the outcomes of 3 regressions, which are here. And each and every time I'm plotting the estimates corresponding to the factorized variable x, okay? And this is really nice because we can immediately see the differences between the regressions and the outcomes, and there's just a myriad of applications. Obviously, you can think of difference in differences models, regression discontinuities, regression kink designs. All these can be operationalized with the plot B command. You can also think about heterogeneity analyses, kind of thinking how the outcomes of interest differ between different people with different characteristics. And you can also think about specification testing and robustness, right? How different variations on your principal specification could potentially affect your results. So this is really nice. And as I said, this is done extremely fast, which is the key advantage of this package. Now, just to illustrate this, I'll be benchmarking the plot command against Stata's native command. And here, what I'll be doing, I'll be replicating the graph which I showed you in the first example. So that's the 2 histograms combined, okay? And what I'll be doing is I'll be running the plot tabs command, which produces this chart. And then I will be also running the native Stata command, which is 2-way and histogram. Okay. The chart here compares the execution times of the 2 types of commands. And I should note that the only way how to meaningfully illustrate the relative performance of these 2 commands is on a logarithmic scale. So this is log 10 scaling, which is very different from arithmetic, obviously. But arithmetic graph just didn't make sense for this one. So what I did was I ran these 2 commands with different numbers of observations, ranging from a few thousands to 250 millions, which might sound like a lot, but I'm really using these data sets quite a lot, even on the far right end of the spectrum. And what you can see from the chart is that the plot tabs command always manages to produce the graph under a minute. In fact, even when we are going close to 250 million, the computation time is about 30 seconds, right? Because this is, again, log scaling. So this is a very fast computation. Now, compared to the 2-way histogram, that one takes 2 hours, almost 2 hours, right? So we're talking about efficiency gains in the order of like 240 fold compared to the native routine. So that's quite something, and I'm very happy with the commands that I produced. But basically, this is what I have to say. So let me just conclude and mention a few more things. First of all, I hope that I have illustrated that the efficiency does actually matter, not only from the perspective of their comfort, but also in terms of kind of the broader implications for the carbon footprint and all the related issues. And if you ask me, I believe that optimizing software packages might really just be the most environmentally conscious thing that we as individuals will ever do. Like, sure, you can change your routines, you can fly less, but if we are talking about larger impact, this is quite a low-hanging fruit. Now, the family of commands that I've produced may be a little bit quirky in terms of the syntax. It definitely does not conform to the traditional Stata style, but it does highlight the efficiency gains that can be reaped by bypassing these old bottlenecks that are sometimes still present in Stata. So rather than advocating its use, this is more of a proof of a concept and kind of an illustration where I would like Stata to focus some of their energy, because I think that they could make quite a big difference. Now, I will end with a disclaimer, and that is that I do not really have the skills to turn this plot family of commands into something that is more user-friendly and also kind of available at SSC, having help files and all that sort of stuff. So, I mean, if you do like what I have done with these charts and you would like to help me with turning them into something more proper, please do get in touch. But other than that, let me just say that, yeah, I think that we can make Stata much faster. Sometimes it's really, really simple. And I believe, especially these preserve, restore bottlenecks are not endemic to graphing commands. There are other commands which could be easily adjusted to avoid this computational or memory intensity. Commands like outrag, for example, which is really popular, it does suffer from the same issue. And I'm sure that there will be others. So if we can comb through the Stata kind of quiver of commands and make them more efficient, that would be amazing. And yeah, thanks a lot. By the way, I also do have quite a lot of Stata tips on my website, which you can just find if you Google my name. And if you have any questions, feel free to ask them, although I'm not really sure whether there's a lot to discuss. So thanks.
Jan, thank you for that. That is actually really impressive what you've shown there. I had to look at that last graph a couple of times, and then as you said, it was a logarithmic graph, and I'm like, okay, they are significant improvements. So we have got a few questions on here, and we've got 5 minutes for questions before we head off for our afternoon tea break. We've got a question here from Austin Nichols. Would love to see a comparison to GR7 here.
Mm-hmm. Mm-hmm. I'll try to do that. I have to admit that I do not know that command, so I'll check it out for sure.
Okay, and then we have a comment from Simon Turner. This was superb. So you've got a fan in Simon. He's then got a question: how does it actually do? How does it do it? So how do your graphs actually get such significant savings?
Right. So let me see. For multiple frames, or just using frames to preserve, restore. So right now I'm graphing from a dedicated frame. There's just one frame that is basically holding all the lines that are graphed. So in reality, what is happening under the hood is that I have the X variable, right, which I assume is shared by all the Y variables, like, you know, in terms of the X and Y correspondence. And then when I add another line to this plot tabs, what happens under the hood is that this line is basically merged one-on-one on the X variable with the old graph that is already in the separate data frame. So you're basically merging and merging and merging more and more graphs. And there are different ways how to operationalize this, and some of them will be better than what I have done so far. But yeah, this is kind of the underlying logic.
Very, very impressive. So we've got a comment here from Austin. GR7 is the Stata 7 graphics. It's preserved for those of us who still remember how to use them. SysUse followed by GR7 MPG will give you a much faster but less pretty histogram. So
that's interesting.
I'll have to try that one. I've got Stata open on my computer. I'll try that during the afternoon tea.